Good afternoon, Doctor. We are Group 10. Now, our topic for today is equilibrium change for reaction, phase rule for chemical reacting system, and multiple reactions equilibrium. Now, for our first of all, I would like to introduce our group members. My name is Steven and Celebrian Scutad. My number is 15666. And then the second one is Muhammad Arish bin Yusran Nadizri 199018. The third member is Bita Abidi 204364. For the last member is Yo Winfing 203127. Now, for the first topic, I will discuss the equilibrium change for the reaction. So, for the equilibrium change for the reaction, it revolves into the Le-Chatter's principle. So, let us give a brief description. What is Le-Chatter's principle? It states here that if a dynamic equilibrium is disturbed by changing the conditions, these are the pressure, temperature, and concentration, the position of equilibrium shifts to counteract the change to re-establish an equilibrium, which means it can go either left or right position. So, our first condition, I will discuss the concentration changes. Le-Chatter's principle states that if the system is changed in a way that increases the concentration of one of the reacting species, it must be favor the reaction which species is consumed. In other words, if there's an increase in products, the reaction quotient is increased, making it a greater equilibrium constant. So what happens if we increase the concentration? So from the principle, in this case, as you can see the first image, the equilibrium position will move so that the concentration of A decreases again by reacting it with B to form C and D. The equilibrium moves to the right as you can see the green arrow below. Now, what if we decrease the concentration? What will happen? In this opposite case, in which the concentration of A is decreased, according to Le-Chatter's principle, the position of equilibrium will move so that the concentration of A increases again. More C and D will act to replace the A that has been removed. As you can see in the second diagram, the position of equilibrium moves to the left if you decrease the concentration of A. Now, let us go to the second condition, which is the pressure changes. So, how will the pressure change if we change the condition or we increase the pressure? So, we have to assume that this only applies, or let us put in our let's just say in our system that this only applies to reaction involving gases, although not necessarily all phases in the reaction need to be in the gas phase. So there's a general homogeneous reaction given in this equation. So as I mentioned, as we increase the pressure is increased if the position of equilibrium will move so that the pressure is reduced again. The pressure is caused by gas molecules hitting the size of their container. The molecules in the container, the higher the pressure will be. The system can reduce the pressure by reacting in such a way to produce a fuel. So in the pressure changes, you can see the diagram. In a diagram, the green arrow moves to the right. This is the condition when we increase the pressure on the reaction. Now, if we decrease the pressure, what would happen? So the equilibrium will move in such a way that the pressure increases again. It can do that by producing the more gaseous molecules, and the position of equilibrium moves over to the left side of the reaction. So as you can see in the diagram, the position of equilibrium moves to the left if you decrease the pressure of the reaction. Now to the last condition, which is the temperature of changes. To understand how temperature change affect the equilibrium condition, the sign of the reaction enthalpy must be known. Assume that the heat for reaction is exothermic, which means heat is involved or heat is evolved. Sorry. So what will happen if we increase the temperature? If the temperature is increased, then the position of equilibrium will move so that the temperature is reduced again. Suppose if the system equilibrium at 300 degrees Celsius, temperature is increased to 600 or 500. To cool it down, it needs to absorb an extra heat added. In this case, the back reaction is that when which heat is absorbed, the position of equilibrium therefore moves to the left. The new equilibrium mixture contains more A and B, less C and D. As you can see in the first diagram of the increase of temperature, you will see that the left arrow will be going from right to left. So the goal is to maximize the amount of C and D, increasing the temperature under reversible reaction in which the forward reaction is exothermic is a poor approach. So let us take note of that. So for the decrease of temperature, the equilibrium will move in such a way the temperature is increased. Again, suppose the another assumptions that if the system is equilibrium at 500 degrees Celsius and the temperature is reduced to 400 degrees Celsius, the reaction will tend to heat itself up again to return the original temperature by favoring the exothermic reaction. The position of equilibrium will move to the right with more A and B converted into C and D, lower the temperature. So the green moves from left to right when we decrease the temperature. So that is for my part, Dr. Hikal. And now I will move and I will pass it to Miss Beta to discuss the uh, phase rule for the chemically reacting system. Miss Beta?
Thank you very much, Stephen. All right, as for my part, which is phase rule for the chemically reacting system, we know that chemical reaction equilibrium calculation is usually based on thermodynamic properties. So as we know, Gibbs energy is not dependent on the reaction path used. Equilibrium calculations on reacting systems should be performed on sets of independent reactions. As long as we consider the largest number of linearly independent chemical reactions possible for the species present, it doesn't matter which set of reactions we actually considered. We can use the Gibbs phase rule to find the number of independent chemical reactions. This could be obtained by counting the total number of variables in the system and making sure we have the same number of independent equations. So the number of independent chemical reactions, which is denoted by R, needed to specify the system is given by R is equal to number of chemical species minus degrees of freedom plus 2 minus the number of phases in the system minus stoichiometric constraints. Next slide, please. All right. So as I already explained, which all of these symbols denote for. This equation, it helps us find the number of independent reactions that we need to specify among the chemical species present. In addition, the inlet conditions dictates the stoichiometric constraints. The solution of the multiple reaction equilibria problem will give us the equilibrium composition of the system as long as the reactions we come up with are independent. Lastly, and furthermore, if different sets of independent equations were chosen, which satisfy the number given by the equation, the same result would be obtained for the equilibrium composition. That's all from me. I'm going to pass it to Wang Feng. Thank you very much.
Thank you, Bita, for the awesome presentation. So for my part, I have multiple reaction equilibrium. So what is multiple reaction equilibrium? Here we have the explanation, which is if the reaction can be expressed as a sum of two or more reactions, the equilibrium constant for the overall reaction is given by the product of the equilibrium constant of the individual reaction. So we can see down here, we have two reactions for this example. So the overall equation is the third one, AB equals to E plus F, and we have three equilibrium constants for each reaction. So for the overall reaction equilibrium constant, we have to multiply both individual equilibrium constant, which is K prime C, minus multiple by K double prime C. So the next page, please. So this is the example for the multiple reaction equilibrium. In this example, we have two individual reactions and one overall reaction. So we have the first individual reaction, and we have the equilibrium constant of 2 times 10 power of negative 25, and the second reaction with the equilibrium constant of 6.4 times 10 power of 9. To find the overall equilibrium constant, we have to do as a follow. K is, we have the constant expression for the reaction right here, K1, K2, and K3. So to get K3, we have to multiply K1 and K2, and we will get 1.3 times 10 power of negative 15. So I've done my presentation. I will now pass the application to Aras.
Hello. So for the application, we're going to show how Le Chatelier's principle can be used in the industry. So in this example, our application now is to produce methanol production. And we can see here the chemical reaction for it. And yes, the methanol is used in fuel mixtures and also is very important for the commercial chemical. And the reaction parameters for producing this methanol are maintained by the temperature by using the catalyst of the reactor pressure at 5 megapascal to 10 megapascal. So in the reaction scheme, we can see that 3 moles of synthesis gas is required for making 1 mole of methanol vapor, which we can see that it is further condensed to liquid state by going through the condensing process. And by this principle also, it leads to the application that the high pressure maintenance is the main parameter for the formation of the products. And the inclusion of smaller amount of catalyst with moderate temperature maintenance favor the product formation of methanol. And as you can see down there is the kinetic expression, which is based on the pressure. So I guess that's it. I'm now moving to the summary of our presentation. So from our presentation, we can have a look at the equilibrium change for the reaction. It tells us about the Le Chatelier's principle. And if a system at equilibrium is disturbed by change in temperature, the pressure or the concentration of one of the components, the system will shift its equilibrium position so as to counter react the effect of the disturbance. So the next one, it tells us about the Gibbs phase rule, which is on the chemically reacting systems. It provides the theoretical foundation based in thermodynamics for characterization the chemical state of a system, predicting the equilibrium relations of the phases present. And the last one is the multiple reaction equilibrium. And this reaction, it can be divided into 2 or more phases in multiple equilibrium. Both stages must be considered in calculation for the equilibrium constant. And the equilibrium expression of the overall reaction is equivalent to the product of the equilibrium constant for each state in a reaction mechanism. So by that, we end our presentation. I would like to thank Doctor and thank you very much.